Hello and welcome back. We are very glad to see you, and big thanks to all of you who have subscribed to our channel since our last video. Today we are going to learn about resistors in series and in parallel, what is their function in electrical circuits, and is it such a good idea to build custom power source using resistors in series as voltage dividers. If you enjoy practical electronics tutorials like this one, please subscribe to the channel. Don't forget to like the video and enable notifications so you don't miss future projects. Thank you. By definition, two or more resistors that share same current running through them are considered resistors in series. Also, voltage drop across each resistor is proportional to value of that resistor. Analog to that, resistors in parallel share the same voltage across their terminals. In this case, the current running through each resistor is proportional to the value of that resistor. For both resistors in series and in parallel, their number and value can vary depending on design requirements and other parameters of electrical circuit. Next thing that is very important to learn is that, resistors in series and in parallel have another important feature, and that is their equivalent resistance. For resistors in series, the math is pretty simple. If we were to replace all 9 resistors with just one, its resistance would simply be the sum of resistances of each individual resistor R1 to R9. For resistors in parallel, math is a little bit more complicated, but not by much. If we were to replace all 9 resistors with just one, its resistance would be inversely proportional to sum of inverse resistances of each individual resistor R1 to R9. Okay, today resistors come in all shapes and sizes, with myriads of resistance values to choose from, so why would there ever be a need to put 2 or more resistors in series or in parallel? Well, first reason is ubiquity and price. Common 1/4 watts resistors, like the ones on the photo, are very inexpensive and very easy to obtain. Putting them in series or in parallel gives you the opportunity to combine them in every desirable value of equivalent resistor you can imagine or need. Next, resistors in series give you the opportunity to build custom voltage drops and custom voltage reference points in your circuit. Analog to that, resistors in parallel give you the opportunity to divide power source current into as many as needed individually tailored current values, per your circuit design requirements. Next is the heat dissipation. If your circuit design requires high currents, heat dissipation is a major problem to address. Combining resistors in parallel mitigates the problem of heat dissipation, allowing more resistors to divide burden of heat dissipation amongst themselves. But there are also some cons of using resistors in series or in parallel. Using many resistors rather than dedicated one complicates circuit design, and introduces greater possibility of error in calculation. Next, more resistors require more space, so need for a larger footprint is introduced. This causes increase in bill of materials. Now, all this theory is nice and fine, but let's see some practical problems where we can apply resistors in series and in parallel to solve real-life problems. Let's solve problem of powering up 100 LEDs. If you are a regular viewer of our channel, you are already familiar with LEDs, their properties, and electrical characteristics. If you are new to our channel, here is a quick reminder of electrical characteristic of an ideal LED. First, 2 most important characteristic of any LED are, voltage drop, and maximum current allowed. Each LED in circuit introduces voltage drop between 1.8 and 3 volts, depending on the type of diode and its size. Also, let us remind ourselves that voltage drop across any component is the measure of resistance with which that component pushes against power source. Next, for most visible light spectrum LEDs, the maximum current that diode can theoretically sustain indefinitely is 20 mA. This amperage gives us the maximum glow for each LED. We have also learned that in order to prolong LED life and mitigate heat dissipation, half of maximum current value is recommended in real-life scenarios. Also, there is a design request of an adequate power source. And at last, we have to take into consideration heat dissipation for every component. So, are we going to daisy chain our LEDs in series, or are we going to place them in parallel configuration? Answer to this question depends on available power source. Let's say we have 5 volts power source. Most 5 volts power sources will have no trouble delivering 20 milliamperes as required to power each LED individually. If we were to switch on this circuit, nothing would have happened. But why? Let us remind ourselves that each LED introduces voltage drop of 3 volts. Therefore, combined voltage drop across all LEDs is 300 volts. Again, there is 300 volts of force of combined LEDs pushing against our 5 volts power source. In this scenario, there will be no current running through the circuit and all LEDs will remain dark. Common current in the circuit will be 0. So, our only option is to put our LEDs in parallel. Now, we have reconfigured our LEDs in parallel, so problem of voltage drop is solved. All LEDs combined now introduce only 3 volts of voltage drop, because they are in parallel and they all share the same voltage as power source. But now there is another problem. We have to introduce current limiting resistors for each individual LED. Simple Ohm law equation gives us required value of 100 ohms for each individual current limiting resistor for each individual LED. All combined currents in the circuit add to 2 amperes. Most 5 volts power sources can sustain this amperage without serious overheating, so we are good. Next, we have to calculate heat dissipation for each resistor. Using formula for power calculation, we get that each resistor has to dissipate 100 milliwatts of power, which is well within resistor heat dissipation parameters, less than 125 milliwatts maximum heat dissipation allowed, so we are good. From electrical point of view, this design is sound. But there are cons. First, we need 100 pieces of 100 ohms resistors put in series with each LED. This introduces cost. Also, the resistors require space, so we are increasing the necessary footprint for circuit implementation. All of this introduces increase in bill of materials. Now, the most logical and most obvious question is, could we replace these 100 resistors in parallel with just one equivalent resistor? Let's do that, and see where the math takes us from here. The formula for calculating equivalent resistor for resistors in parallel is on the screen. It says that inverse value of equivalent resistor is equal to sum of inverse value of each individual resistor in parallel. So, the math says that we can replace all of our 100 pieces of 100 ohms resistor with just one resistor with resistance of 1 ohm. So far so good. So, our revised schematic would look something like this. In ideal scenario, 2 amperes of power from power source would split equally through each of 100 branches, and deliver 20 milliamperes of current for each individual LED. In real-life scenario, there are no 2 identical LEDs, so there would be some branches with more, and some with less than 20 milliamperes of current, but the end sum of all currents would be the same, 2 amperes. Now obvious problem is 1 ohm resistor. It needs to dissipate 4 watts of power. Although there are 1 ohm metal oxide resistors available for purchase, that can dissipate more than 1/4 watts of power, they are expensive and bulky. So, we are definitely not good here. This is one good example where breaking up one special resistor into more common resistors placed in parallel configuration is sound solution to design problem. Now, let us get back to problem of placing 100 LEDs in series. From before, we have learned that placing that many LEDs in series would require DC power source that can deliver at least 300 volts. But there is the problem. Most DC power sources can deliver up to 50 volts, everything above that is for industrial use and not easily available for individual purchase, and they are pricey. But there is something in our household that we can use. A wall socket. It can deliver 230 volts. But, how does that help us? Wall socket delivers AC power, and we need DC. Now, we must emphasize that we adamantly advise against building this circuit in real life, as it can do you harm. Wall socket can provide excess of 10 amperes of current. If something goes wrong with implementation of the circuit, there can be serious consequences. Please do not try this at home. If we were to source 230 AC volts from wall socket and place 400 volts rectifier diode, we would get 325 volts of DC power. Have in mind that AC voltage of AC power source is root mean square of equivalent DC voltage of DC power source. Also, we need to place 47 microfarad capacitor, rated for 400 volts, in order to flatten sine oscillations inherited from AC power source and make up for missing negative portions of AC sine wave. From before we know that equivalent DC voltage is 325 volts. Desired current is 20 milliamperes, so let's calculate value of resistor R. By using Ohm's law, we get that we need 215 ohms resistor. Let's also do heat dissipation calculation. So, our resistor would need to dissipate around 1/2 of watt. So, we are not good. First, we have a non-standard value of 215 ohms for resistor, and then the requirements for heat dissipation are more than 3 times more of what our common resistor can provide. So, how can we mitigate this problem? As mentioned before, one of the perks of placing 2 or more resistors in parallel is that they can divide heat dissipation requirement of equivalent resistor among themselves. If we could split resistor R into 4 resistors in parallel, each resistor would need to dissipate approximately 0.13 watts, which is within tolerance limits. So, let's do some math. If we put 4 common 1 kilo ohms resistors in parallel, their equivalent resistance would be 250 ohms, which is pretty close match to our desired value for resistor R. Also, each resistor Rp now dissipates approximately 0.13 watts of power. So, now, we are all good. Now, let's do some cheats. From before we have learned that formulas for calculating equivalent resistance for 2 or more resistors in series and in parallel are as displayed on the screen. For resistors in series, the equivalent resistance is sum of each individual resistance, and for resistors in parallel, inverse value of equivalent resistance is equal to sum of inverse values of each individual resistance. There are also some special cases, when all resistors in series or in parallel have the same value. In such special cases the formulas are simplified. Also, one more important thing to remember is that resistors in series divide voltage, while resistors in series divide current. If you want to be fancy, when marking that 2 or more resistors are in parallel, you can use following notation as displayed on the screen. Now, we would do our viewers a disservice, if we would skip to mention one more special case of resistors in series and in parallel. That case is when one of the resistors in series or in parallel is 10 times or more larger than the other one. Just now, we saw what happens when resistors have the same value. The math simplifies and equivalent resistance is easier to calculate. Now, let's see what happens when value of resistors differs by scale of 10 or more. Let's define that resistor R1 has value of 10 kilo ohms, and resistor R2 has value of 100 kilo ohms. Let's also define 5 volts DC power source. Now, without any calculation we will assume that equivalent resistor Req has value as same as resistor R2, 100,000 ohms. By using Ohm's law let's quickly calculate voltage drops and currents for each circuit. We can conclude that when the difference between resistors in series or in parallel are at least 10 times or more, for resistors in series we can discard lower value resistor, and for resistors in parallel we can discard higher value resistor. Error introduced in both calculation is 10% of respective values for voltage drop across resistor R2 in series configuration, and current value for resistor R1 in parallel configuration. If difference between resistors is 20, 30, or 100 times more, the error introduced in calculation is even more negligible. Now, if you have studied electronics, or you like it as a hobby, you might have crossed paths with some schematic similar to this. The point of this sick and deranged exercise in futility is to find equivalent value, if all resistors in the circuit are the same. So, let's dispatch with this mental illness and bring some sanity back. First of all, no sane person would ever consider this a good and practical design. Second, learning about electronics should be fun, not gateway for those individuals who wrongly wear title of educators, to heal their life inadequacies on young pupils and students by introducing this abuse and harassment in learning process. If your educator presents you with this or a similar problem, please refer them our way, so we can enlighten them and demonstrate the power of prayer in design and implementing electronic circuits. Now, that this pet peeve of ours is out of the way, let's get back to voltage dividers. By definition, two or more resistors placed in series make voltage divider circuit. This is the simplest version, containing power source, and two resistors. Both resistors share common current I. The function of resistors R1 and R2 is to divide voltage VCC across their respective terminals, proportionally to their values. We call these division voltage drops. Let's mark them U1 for voltage drop across the resistor R1, and U2 for resistor R2. It is a matter of simple math and application of Ohm's law to calculate values for voltage drops U1 and U2. Now, let's rearrange these formulas and calculate current I. Now, since both resistors share the same current, let's set an equality for I. Then let's rearrange this, so that we have voltage drops on one side, and resistance on the other side of equality. So, how do we read this proportionality? It says, smaller resistor causes smaller voltage drop, larger resistor causes larger voltage drop, and that is all there is to it. Now, let's see if it is a good idea to use resistors in series to create custom adjustable DC power source. Let's take 5 volts DC power source first. If you want, you can choose any other power source available to you, the principle is the same. We will choose 5 volts, as it is very accessible and ubiquitous power source. We all have smartphones, so we all have some chargers we can utilize for this little project. Now, idea is to use 5 same value resistors in series, and divide output from our power source into 5 equal parts, with each part having voltage drop of 1 volt. By dividing 5 volts power source like this, we can use points A to E to select voltages ranging from 1 to 5 volts, in respect to negative terminal, or commonly referred to as ground. So far, so good, but there is a catch. To have an equal 5-part division of our power source, we have to use 5 of the same valued resistors. As common resistors values range from 1 ohm to tens of million of ohms, how do we choose which value is appropriate? Next question is what should be common current, running through all resistors. The answer to that is in maximum heat dissipation parameter for each resistor. Each one of the 5 resistors can dissipate 1/4 of watt of power. Next, each resistor introduces exactly 1 volt of voltage drop across its respective terminals. By utilizing equation for power calculation, to express and calculate current, we get that each resistor can safely run up to 125 milliamperes of current. That is the maximum allowed current through entire circuit. Now, having values for current and voltage drop across the resistor, we can finally calculate the value for each resistor. By using Ohm's law, we get that resistor should have resistance of 8 ohms. Now, since 8 ohms is not common value for the resistor, we will go to next available higher value, and that is 10 ohms resistor. Now, let's recalculate all the values, having chosen 10 ohms for resistor value. Choosing 10 ohms resistor, and having in mind that equivalent resistance of all 5 resistors in series is 50 ohms, we get 100 milliamperes value for current running through the circuit. We also need to recalculate power dissipation for each resistor. Using formula for power calculation, we get that each resistor now dissipates 0.1 watts of power, which is well within tolerance limits. So, now our power source is complete and we can utilize it to power any project that requires 1, 2, 3, 4 or 5 volts of DC power, right? If you can already guess what is wrong with this entire premise and why using resistors in series as voltage dividers to create custom power source is not such a good idea, please leave your explanation in comments section of this video. We would appreciate your feedback very much. Please, before you leave, show your appreciation by liking this video, leaving a comment, sharing it, and please subscribe to the channel. Thank you, and see you next time. Bye.